Okay, so welcome back. We're going to cover section 4.3 now, which is multiplication rules and conditional probability. And so all of the probability that we've done so far, we've just been calculating probabilities of one event taking place. And now we're going to start putting multiple events together, like as in a storyline. And we're going to calculate the probability of this happening given that something else happens. I think earlier I said I got ahead of myself and I started talking about independent events. Independent events are events A and B, and they are said to be independent if the fact that A occurs does not affect the probability of B occurring. And so we'll give you some examples of independent events here shortly. So again, when two or more events are independent, then the probability calculation is simple. You just take the probability of A times the probability of B. Okay, so that's multiplication rule number one. So for example 1, it says a coin is flipped and then a die is rolled. Find the probability of getting a tail and then getting a 4. So obviously whatever happens in the coin flip is not going to affect what happens in the way that the die is rolled. Like they have no gravity over each other or anything. So you just take the probability of getting a tail, which is 1/2, times the probability of getting a 4, which is 1/6, and you multiply those together. So 1/2 times 1/6 is 1/12. Karen, do you want to do example 2?
Sure. So it says a jar contains 3 red marbles, 2 blue, and 5 white. A marble is selected and then replaced, and a second marble is then selected. Find the probability of selecting a red and then a blue marble. Okay, so we want the probability of basically red and blue, is how I'm going to write that notation-wise. So that's just going to be the probability of getting a red one times the probability of then getting a blue one. Okay, so let's see, we reach into our jar, we grab a marble. What's the probability that it's red? Well, there's 3 red ones out of a total of what? 5, 6, 7, 8, 9, 10. So 3 out of 10. Now your key word for this question, I tried to underline it in red for you there, is that it says the first marble was replaced. Okay, that's a really important fact that you have to pay attention to in these questions. So we're putting that red marble back. So essentially now when we go to pick the blue marble, we're like starting over fresh. Okay, so we still have all 10 marbles in the jar, and there are 2 blue ones. So now the probability that we're going to get a blue one is 2 out of 10. So we'll multiply those fractions together and we get 6 out of 100 or 3 out of 50.
Perfect. Okay.
And we'll definitely see some examples where it's not replaced. So we will look at how you handle that.
Yeah. Okay. So in example 3, it says about 9% of men have a type of color blindness that prevents them from distinguishing between red and green. If 3 men are selected at random, find the probability that all of them will have this type of red-green color blindness. Okay, so this is something where because the men are selected at random, the probability of selecting the first man is not going to change the probability of selecting the second, not changing the probability of selecting the third. So these are independent events. And so we follow the multiplication rule. That's just the probability of color blindness times the probability of color blindness times the probability of color blindness. So it just means you're going to take 0.09 times 0.09 times 0.09, and you're going to get a very small number. What is that? 0.09 cubed is about 0.000729. And if you had to round this to the third decimal place, I guess that would be 0.001 or 1%.
0.1%.
0.1%, yeah.
Yeah, and I did show like exponential notation there. So it's obviously not hard to write 0.09 times itself 3 times. But imagine if it said, 100 men are selected at random. You probably wouldn't want to write that out 100 times. So a quicker way of doing it would be like 0.09, and then you just raise it to whatever power is appropriate.
Yeah, that's a good point. Okay, Karen, can you talk about this slide a little bit?
Yep, so when the outcome of the first event affects the outcome or occurrence of the second event in a way that the probability is changed, then the events are said to be dependent events. Okay, and the conditional probability of an event B in relationship to an event A is the probability that B occurs after event A has already occurred. Okay, so you have conditional probability whenever you have dependent events. So the way that we're gonna the notation for conditional probability is P of, and then in the parentheses, we're going to have the B, which is the second event. And then that vertical bar you read as given, and then you put your other event after that. So that notation there, you read out loud or in your head as the probability of B given A. So it's basically saying that you're looking for the probability of B given that A has already happened. Okay, so the second letter, the second event, you're going to assume has already happened. Okay, so for dependent events, our multiplication rule is going to be that the probability of A and B is equal to the probability of A times the probability of B given A. And it seems more complicated when you're just looking at the formula, but it is pretty intuitive when you actually like put it into practice. So let's do some examples here. So example 4 says that 3 cards are drawn from an ordinary deck and not replaced. Find the probability of these events. So getting 3 jacks. Okay, so the probability of 3 jacks. So let's think about this. So we pick a card. What's the probability that it's a jack? Well, there's 4 jacks out of the total of 52, so that would be 4 out of 52. Okay, now we're not replacing that card, okay? So I'm assuming that I picked a jack and I'm holding on to it, okay? Now I go and I pick another card out of that deck. What's the probability that it's another jack? Well, now there's only 3 jacks left, and how many total cards are there? 51. So now your probability is going to be 3 out of 51 for getting the second jack. And then now you're assuming that you're holding on to both of those jacks in one hand. And then you go and you pick a third card out of the deck. What's the probability it's also a jack? Well, now there's 2 left in that deck out of the total of 50 cards. So that's 2 out of 50 for the last one, which is a pretty ugly fraction. And it reduces to 1 out of 5,525. Yes. So the not replaced part is basically the key to tell you that these are dependent events. So since you're going to hold on to that original card, you're now going to alter or change the probability when you go and select the second card.
Yeah, if it had been replaced, then it would have been 4 over 52 times 4 over 52 times 4 over 52, right?
Yep.
Okay. And then it says, what is the probability of getting an ace, a king, and a queen in that order? So the probability of getting an ace is going to be 4 over 52. And then the probability of getting a king is going to be 4 over 51 because we haven't put that ace back in, right? We're still holding that ace. So there's only 51 cards to select from, but there are still 4 kings that we could pick. And then again, there are still 4 queens that we could pick, but now there's only 50 cards left in the deck. And so you get 64 over 132,600, which is reduces to 8 over 16,575. Okay, Karen, do you want to talk about example 5?
Sure. So it says, in a recent survey, 33% of the respondents said that they feel they are overqualified for their present job. Of those, 24% said that they were looking for a new job. If a person is selected at random, find the probability that the person feels that he or she is overqualified and is also looking for a new job. Okay, so we want the probability that they feel overqualified and they're looking for a new job. Okay, so this is going to be according to the formula. This is going to be the probability that they feel overqualified. And then you're going to multiply that with the probability that they're looking for a new job, given that they feel overqualified. Okay, and both of those, pieces of info should be given to you in the problem. You shouldn't have to figure out either of those. So let's see here. So what's the probability that they feel overqualified? Well, that said it was 33%, so 0.33. And then the probability that they're looking for a new job, given that they feel overqualified, well, that's why it says of these, 24% said they were looking for a new job. So that value is 0.24, and then you just multiply those together and you get 0.079. Or if you want to put it back into a percent, that would be 7.9%.
Okay, great. Okay, so now it says a bag contains 9 red marbles, 8 white marbles, and 6 blue marbles. Randomly choose 2 marbles one at a time without replacement. Find the following. The probability that the first marble is red and the second marble is white. Okay, so the probability that the first marble is red is going to be, well, there are 9 red marbles, 8 white marbles, and 6 blue marbles. So altogether, that's what? 17, 23. So I think it's 9 out of 23 that the first marble is red. And then the probability that the second marble is white, given the first marble is red, is going to be, well, there's only going to be 22 marbles left, and there are 8 white marbles, so that would be 8 over 22. And so then we multiply those two together, and we get 36 over 253. Karen, do you want to do B?
Yeah, so I was just going to point out on part A, like I wrote it out formally with like, proper notation as far as like P of R times P of, W given R. If you like using that notation and it doesn't confuse you, then go for it, do that. But I mean, like I think Dr. Insko just kind of figured it out pretty much, just step by step there rationally. So you don't necessarily like have to write all of that notation down. You're intuitively using it when you answer these problems. Okay, so part B says the probability that both are the same color. Okay, so now we have to think about, we got to get a little creative here. We got to think about all the ways that you can have 2 marbles of the same color. So you could obviously have 2 reds, 2 whites, or 2 blues. Okay, so we have 3 different outcomes that would satisfy that event. So now we're going to figure out the probability for each one of those outcomes. So the probability of red and red. Okay, so what's the probability we get a red marble? Well, that's 9 out of 23. If you're holding on to that red marble, then the probability of getting another one is going to be 8 out of 22. Okay, then for white and white, and since basically we're adding up like these individual outcomes that, I said the keyword there. I guess there's no real other way to say it. Since we're putting together all of these different outcomes that can satisfy the event, basically the word or means that we're going to add up all of those in between. Okay, so for white and white, let's see, it'd be 8 out of 23 for the first marble. And then if you're holding that white marble, the next one would be 7 out of 22. And then we'll add that with the probability of getting 2 blue ones. So that would be 6 out of 23, and then 5 out of 22. And you figure out what all of that adds up to, reduce your fraction, and you should get 79 out of 253.
Perfect. Okay. So for part C, we're asked to find the probability if the second marble is blue. Okay, so you're kind of ignoring what the first one is there in that statement. So you have to kind of assume, well, it could be red and blue, or it could be white and blue, or it could be blue and blue. And now these are not necessarily independent events, are they? Or are they? I guess they are.
For what? Like,
so red and blue, you get, I can see how you get 9 out of 23 times 6 over 22. And then white and blue, well, there's 8 out of 23 is the probability that you pick a white, and then 6 out of 22 for blue. And then the next one is 6 out of 23 times 5 over 22. Okay, I see how all that works. And then since those are mutually exclusive events, you just add those up and you get, I guess it reduces to 6 out of 23. Is that right?
yep.
Perfect. Okay. And then example 6, you want to walk us through this one?
Yeah, so this says, all right, box 1 contains 2 red marbles and 1 blue. Box 2 has 3 blue and 1 red. A coin is tossed. If it falls heads up, box 1 is selected and a marble is drawn. If it falls tails up, box 2 is selected and we pick a marble. Find the probability of selecting a red marble. Okay, so what I would say for this one, since we've got like boxes and marbles and coins, I would do a tree diagram just to kind of keep everything in order here. So basically we're going to flip a coin and it's going to determine whether or not we select from box 1 or box 2. Okay, so that's going to be my first 2 leaves on my tree diagram. Okay, so what's the probability that we end up selecting from box 1? Well, we have a 50-50 chance because it just depends on what the outcome of the coin is. So the probability that we get box 1 is going to be 1/2. And then the probability that we get box 2 is also 1/2. Okay, now once we pick a box, now we have to reach in and get a marble. Okay, so let's consider all of our possibilities. Well, there's either red marbles or blue marbles. So off of each one of those boxes, I'm going to do 2 leaves for red and blue. And then let's figure out the probability of along each one of these. So the probability that we get a red marble, given that we're picking from box 1, well, let's see, there are 2 red out of the total of 3, so that'd be 2/3. Probability we get a blue marble from box 1 is the 1 out of the 3, because there's only 1 blue. And then let's go to box 2. So probability we get a red marble from box 2, there's 1 red one out of the total of 4, so 1/4. And then the blue marble is 3 out of 4 if we're in box 2. Okay, so let's write out all of these possibilities or outcomes now. So the probability that we select box 1 and we get a red marble is going to be 1/2, because that's the probability that we get box 1 in the first place. And then you're going to multiply that with the probability of getting a red marble from box 1. So times that by 2/3 and you get 1/3. Okay, then we'll do the probability of box 1 and blue. So that's the 1/2 times 1/3. And then box 2 and red would be the 1/2 times 1/4. And then the last pairing is box 2 and blue. So we do the 1/2 times the 3/4. Okay, now I haven't actually answered the question at all. I simply just kind of laid out all of my possible options for what can happen with this scenario. So what did they want? Find the probability of selecting a red marble. Okay, so probability of red, we basically just want to gather up the outcomes that had red in them. So we're going to take that 1/3, add it to the 1/8. So the box 1 in red plus the box 2 in red. So 1/3 plus 1/8, which comes out to be 11/24.
Perfect. Okay, so we're going to do another probability tree here. Here things are not just 50-50. So let's read the problem. It says a production process produces an item. On average, 15% of all items produced are defective. Each item that is inspected before being shipped, and the inspector misclassifies an item 10% of the time. Okay, so that's interesting. So there's an inspector, and he's deciding whether it's good or bad. And I guess we're saying that 15% of all items produced are defective. So let's go through and kind of look at this.
This is like a super confusing problem.
Right.
But it's like one of the few that we actually have to choose from when you make the assignments on Connect. So
cool. No, I mean, I get it. So it's like 15% of them are defective. That means 85% are non-defective. But then whenever the inspector looks at something, there's a 10% chance that the inspector is going to get it wrong. So of the defective ones, 10% he may label as good, which means that 90% are labeled as bad. So he's correct 90% of the time, right? Of the non-defective ones, well, 90% of the time he's going to say that they're good because he's wrong 10% of the time. And the other 10% of the time he's going to label them as bad, even though they were non-defective. So then the probability of being defective but being labeled good is going to be 0.15 times 0.1. So that'll give you 0.015. You guys see how that calculation goes? You're just working down the tree. So what's the probability of defective and being labeled bad? Well, that would be 0.15 times 0.9, right? And so that gives you 0.135. Karen, do you want to tell us the probability of being non-defective and being labeled good?
Yeah, so that would be the 0.85 and then the 0.9 on that branch, multiply those, you get 0.765, and then non-defective and bad would be the 0.85 and the 0.1, so 0.085.
Mhm. Cool. I think this example is confusing is important because this happens in medicine a lot where people are sometimes, they show the symptoms of having a disease, but then they're misdiagnosed like 10% of the time. And so sometimes people are told that they should get a surgery because, 90% of the time people with their symptoms need this surgery. And then sometimes they have complications. Like there might be a 1% chance of complications given that surgery, which then means that there's a small portion of the population that was recommended to get a surgery that they didn't need, and then they suffered complications because of that surgery. I think there's a study that says that the sixth leading killer of Americans is the hospital system. Like they just are told to take certain drugs that they don't need, and then they have complications due to those drugs, or they're told to have surgeries that they don't need, and then they die as a result of the surgeries. It's kind of scary. I don't think the medical industry wants you to know about that, but that's at least it's a statistic I've heard from a reputable source.
I believe it.
Okay, so what proportion of items will be classified as good? Are we going back to the previous example?
Yeah, we didn't answer the question.
I see. Okay, sorry. I just built the table out right. So now
Yeah.
probability of being labeled as good is either defective and good or probability of non-defective and good. And so if we go back to the previous page, that was 0.015 for defective and good and 0.765 for non-defective and good. So you add those together and you get 0.78. So 78% of the items are labeled as good. Oops.
Yeah, and we can't answer part B yet until we learn one other thing. So we'll come back to that.
Okay, so that's what is the probability that an item is defective given that it was classified as good? Okay, so now we're going to learn about conditional probability, a formula for conditional probability, right?
Yeah, we already mentioned what conditional probability is, and we wrote out the formula for dependent events. And this is just that same exact formula, just rearranged. So all we did was solve for the conditional part. So the probability of B given A. So that's just going to be equal to the probability of A and B divided by the probability of A. So again, it's not technically a new formula. We already used it. We just rearranged to solve for a different part of it. So example 7 says that the probability that Sam parks in a no parking zone and gets a parking ticket is 0.06. The probability that Sam cannot find a legal parking space and has to park in a no parking zone is 0.2. On Tuesday, Sam arrives at school and has to park in a no parking zone. Find the probability that he will get a parking ticket. Okay, so we want the probability that he gets a parking ticket given that he parked in a no parking zone. Okay, so just to clarify, my T stands for that he gets a ticket and N means that he parks in a no parking zone. Okay, so according to the formula, so let me just mention this. So the probability, the conditional probability, basically like it's just the probability of both of them happening on top. So the probability of N and T, or you could write that as the probability of T and N. Okay, the order that you write an and statement doesn't matter. So either one of those would be fine. But which letter is on bottom? Like Dr. Insko, if I were to ask you like, how do you match this up if you want to kind of memorize like which letter do you divide by? Is it the first one or the second one?
You divide by the one that's after the vertical bar. So it's
yes.
The probability of B given A, you divide by the probability of A.
Yes, exactly. Okay, so the order of the letters on top doesn't matter. The important thing is that you know that you're always dividing by that second letter. Okay, it's the one that you're assuming has happened. It's the given one. Okay, so we're going to divide by the probability that he parked in a no parking zone. Okay, so they should give us both of these. So it should be an easy question from here. So it was a 0.06 probability that he parked in a no parking zone and got a ticket. And then the probability that he had to park in a no parking zone is 0.2. So it's just 0.06 divided by 0.2, which comes out to be 0.3.
Cool. Okay. So now that we have that formula in hand, we can now go back and do problem B. That was, what is the probability that an item is defective given that it was classified as good? Okay, so now what we're going to do is we're doing probability of D given G. The probability of D and G, I think, was 0.015. And then the probability that it was good was 0.78. So we just take probability of D and G divided by probability of G, and you should get 0.019.
Yeah, where'd you get the 0.78 from?
The 0.78, the probability that was good, that was from part A, right? We calculated that in part A, going back a few slides, where we took the probability of D and G or the probability of N and G and added those up to get 0.78. So that was the probability of just getting good.
Cool.
Being labeled as good. Okay. So what this is saying is that, like, let's read that again. It's the probability that the item was labeled as good, but it is defective. So this means that this factory is sending out a defective item that they think is good. What is that? That's 1.9% of the time. No, yeah. 1.9% of the time, right? So 0.019 for a probability is 1.9%. So almost 2% of the time they're sending out bad products. Okay, example 8.
Yeah, so this one, we're going to look at how to do like conditional probability when we're given like tables of information now. So this one says that a recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. The results are shown. Find the probability that the respondent answered yes, given that the respondent was a female. Okay, so let's put that kind of into the formula form. Okay, so this is the probability that they answered yes, given, which means I'm going to put a vertical bar, and then the F after that. Okay, so then according to the formula, that's going to be the probability of female and yes divided by the probability of the given one. So divided by the probability that they are female. And then we should just be able to kind of look at the table and get these numbers. So female and yes is where the female row overlaps with the yes column. So that's 8 out of the total of 100 from that table. And then the probability that they're female is the total for the female row, which is 50 out of the 100 total. Okay, and then you'll notice that that looks ugly because we have like 2 fractions inside of a larger fraction, but both of the denominators are the same, so they essentially just cancel each other out. So 8 divided by 50 reduces to 4 out of 25. Now, do you have to use that formula? No, okay? You can just more intuitively like look at your table and figure it out in kind of a quicker way. So here's how I would approach this question. We're looking for the probability that they answered yes, given that they're female. So what you want to do is go 0 in on what the given part is, okay, whether it's a row or a column. So given that they're female. So what I normally do with these questions is I would go say, all right, I just want to look at the female row. Okay, so I'm just going to circle that female row, and then I'm only allowed to use numbers from that row, okay, because that's my given part. That has to happen. So now what's the probability that the person answered yes? Well, there's 8 that answered yes out of the total for that row, which was 50. So either way, you're getting 8 out of 50 and reducing that to 4 over 25.
Okay, great. So then in part B, it says the respondent was male, given that the respondent answered no. So what was given is that they answered no. And so we want to look at the no column now. And then we just want to calculate, using the trick that Karen just told us, to calculate the probability that they were male, given that they said no. Well, then that just means you look at the no column and you take the males, which is 18, divided by the total in that column, which is 60. So you get 18 over 60, which is 3/10. Is that good?
Yep.
Okay. So now probabilities for at least. I think we're going to use some conditional probabilities here, or complements here. So probability at least 1. We're going to use the complement rule here. So you take 1 minus the probability of none.
Yeah, so hold on, let's just think about why that's the complement, because that's kind of confusing to students at first. So why is the the complement of at least one none? So let's say that I told my class that at least one of you will get an A. What's the only way that I'm wrong?
That none of them got an A.
Yeah. If one of them gets an A, I was right. If 2, 3, 4, up to all of them get an A, I was still right. The only way I'm wrong, so in other words, the opposite basically, is if no one gets an A. So whenever you're finding the probability of at least one thing happening, and it has to be a 1, then you can use this complement rule, which says that that's going to be equal to 1 minus the probability that basically the event doesn't happen at all.
So then probability of at least 2 is 1 minus the probability of none, or 1, right?
Yeah, we're not going to get there until chapter 5. We'll learn the binomial distribution. For now, in this section, we're only going to mention at least 1.
I think that's why I was confused, because I was like, why are we only covering this one case? But now I got what you're saying.
Yeah.
Okay, so a person selects 3 cards from an ordinary deck and replaces each card after it is drawn. Find the probability that the person will get at least 1 heart. Okay, well, probability of at least 1 heart is equal to 1 minus the probability that you get no hearts. So what's the probability that you get no hearts? Well, there's 39 over 52 times what? 39 over 52.
Yeah, where are you getting 39 from?
39 over 52. I think that's 52 minus 13, right? So there are 13 hearts. And so we're subtracting off those and we're left with 39. So there's 39 cards that are not hearts in the deck. And then because we're replacing them, we're getting 39 over 52, 39 over 52, and 39 over 52. Because every time we draw the card, we're putting it back in, right? Does that make sense?
Yep.
Okay. So that's 1 minus 39 over 52 cubed, which ends up being 1 minus 27 over 64, which is 37 over 64. So that's the probability of getting at least 1 heart if you select 3 cards and you're replacing them.
Yeah, so your key word for these questions are the phrase like at least 1. So if you see at least 1, that tells you to use this complement rule. And let's do one more example. So example 10 says that a coin is tossed 5 times. Find the probability of getting at least 1 tail. Okay, so the probability of getting at least 1 tail is going to be equal to 1 minus the probability of getting no tails. Okay, now I didn't really like to say no tails. I kind of just rephrased that for myself. So no tails is the same thing as getting all 5 heads. Okay, so I just kind of rephrased that. Okay, so what's the probability we get all 5 heads? Well, you flip a coin, probability of the first one is a heads is a half, second one heads is another half, a half for all 5 of them. So we have 1 minus 1/2 times itself 5 times, or to the 5th power. So that's going to be 1 minus 1 over 32, which equals 31 out of 32. Okay, and then I just wanted to bring out for you guys something that's going to start happening in your calculators with this section. So because probabilities can often come out to be really small numbers, your calculator actually has a hard time like putting small numbers up for some reason. So for example, like if you do a problem and you were to get this answer right here, your calculator might say 9.48, and then you're going to see like a capital E and then maybe like a -4. Okay, this is not the number 9.48. Okay, this notation here with the capital E is your calculator's way of doing scientific notation. Okay, and it cannot do it for you. Okay, you actually have to sit there and apply the scientific notation. So E -4 means that you're multiplying by 10 to the -4th power, which all in all, that just means you need to move the decimal place to the left 4 places. Okay, so 9.48 E -4, jot that down on your paper, move your decimal place to the left 4 spots. So that's really the number 0.000948. So again, just keep in mind, probability cannot be a number larger than 1. So
Mhm.
If you don't notice the E on the calculator, hopefully you'll notice that 9.48 is kind of a ridiculous answer for a probability. And hopefully that'll kind of train you to go look and say, all right, was there an E on my calculator?
Mhm. Okay. Thank you, Karen. And I think that's it for this section.